Hello and welcome back to Calculus 2. Long time no see, right? We are going to continue with 8.8 with numerical integration. So this is the second to last section in chapter 8. We have one more very important section after this. And then two more sections in chapter 9 and we're done for the second test. Why numerical integration? Well, not every function can be integrated. That's the biggest problem. See, we can differentiate anything, but we cannot integrate anything. We have those methods. They don't cover everything that exists out there, but it's a good chunk. And for some problems, we can't integrate. And because we cannot integrate, we have to resort to numerical method to find area under the curve, which in fact gives us energy or accumulation of some kind. So in order for us to deal with numerical integration, we have to go all the way back when we started talking about integration, because the first two methods of numerical integration were studied all the way back in 5.1. Left and right hand sums were numerical approximations. They are the worst numerical approximations, but they gave us a good insight into what integration is and what we are going to get. So back in 5.1, which is Calc 1, we learned that if we have some kind of a curve f of x between a and b, we can divide into rectangles and then use left sum or the right sum, whatever, to calculate. So here is the left sum. And the way this worked was, this was our x0 value, this was our x1, x2, x3, and in this case x4. We had, in this particular case, four rectangles. Well, you can have, more or less, it doesn't matter, right? And we learned that and that's very important, delta x lengths in each one of these. So your delta x was always xn minus 1, right? So two consecutive ones, and when you subtract them, you get delta x. So what we defined as the definite integral in Calc 1 was this. You take your function at xn, whether it's x1, x2, x3, I don't care, one of those, and you multiply that by delta x to get one area. So area of one rectangle. So area of one rectangle. Then we add 1 to n, which gives us area of n rectangles. And then we send that n to infinity to give us finally exact area. So what we do in this, and that's how this becomes integral a to b of f of x dx, which we defined as the Riemann integral in Calculus 1. So from one rectangle, which is height times the width, from one integral, then you add a whole bunch of them together, and then you send that finite number n, which in this case our n is 4 because we have 4 rectangles, but right. Oh nice, I just got a ball of popcorn. So now I'll be eating and teaching. That's bad. But I can't resist, so we'll all have to live with it. Perks of, I guess, working from home, right? I can guarantee that at least, you know, a couple of you are watching this on your flat screen TV in the living room, right, at full volume, so the whole neighborhood is engaged. Anyway, so this method introduces error. So all of the purple stuff over here is error. And obviously, because you are approximating, you are not getting exact answers, right? You have to get some kind of error. Exact calculation has no error. Any approximation will have it. So we would like to develop better techniques than the ones we have from before, because the ones from Calc 1 that were sufficient for us to define integral, well, those have a lot of error. So today we learn 3 approximation methods for integration, which introduce a lot less error than what we had in Calc 1. So the first one is Midpoint Rule. Alright, so how does that work? We're going to have some function f of x, and we're going to create, let's put 3 rectangles. We are going to create this interval a to b, which is where we want to approximate the area. So now, instead of picking a left point or picking the right point, we go into middle of our delta x, and we go from there and draw our rectangle. And we do that for every rectangle. And you see that on one side, usually, you gain error in a positive sense, on the other side in a negative sense. They do not cancel each other, but they cancel to some extent. So it introduces less error than if you had, right, the left-hand approximation, which had all of the error present, right? So midpoint will have a lot less error, because error kind of cancels itself, right? Not completely, but a lot of it does. So now, if this is my x0 and this is my x1 and x2, and in this case x3, but it can go as high as you want, we have these important points. And those points are the averages of values, right? So I will have the area be approximated by, in this case, f computed at the average times delta x. So that's my first rectangle. Plus function computed at the average times delta x, which is the width for the other one. By the way, those of you who forgot, delta x is b minus a over n. Right? Delta x is always given by b minus a over n because that's the interval, and then you're dividing that into a finite number of rectangles, which will give you the length for delta x. And finally, for the third rectangle, f of x2 plus x3 over 2 times delta x. So that's why it's called the midpoint. All of these are midpoints. We are calculating function at those midpoints. That will give us the height of the rectangle, and then all you need to do is to multiply by delta x, and you have area. So now, area will be approximated. We can factor out delta x. That's the same for all of these. And inside you just have all of these f's. And you're done. There is nothing more than that. Now there is a cute mathematical formula which you can go ahead and tattoo. But you hopefully know how to compute all of these things. So this is official math formula that tells you that you are calculating the midpoints, you are multiplying that by delta x, and then the summation symbol over here said you are adding how many you have, right? So if you have 6 rectangles, then k goes from 1 to 6, and you will have 6 of these calculations to do. Now obviously what you should do is you should, and again, I don't care if you are computer science major or not, all of you should be able to program this loop in whatever software you like to use, programming language, and just let the computer do it. It's just a couple of lines of code, and it's the most basic thing. So that's the trapezoid rule. Midpoint rule. Trapezoid is next. So for midpoint rule, well, let's do an example because why not? So integrate square root of x from 3 to 7 dx using 3 rectangles. I am purposely using 3 rectangles because 4 rectangles would give me nice divisions. I want to use something crazy. So let's go. You don't have to draw the graph, you can just draw the partition. Here's your 3, here's your 7, and you need to divide it into 3 parts. So each one is 4/3 long. So 3 plus 4/3, well, that's 3 times 3 is 9, plus 4, 13 thirds, plus 4 is 17 thirds, plus 4 is 21 thirds, which is 7. Good. So those are my x0, x1, x2, x3. I need middle points. And those are the averages. So the area will be approximated by delta x is 4/3. Now I have f at 3 plus 13 over 3 over 2 plus f of 13 over 3 plus 17 over 3 over 2 plus f of 17 over 3 plus 7 over 2. So this is where I find all of those midpoints, which are the red dots. And once we have that, we're done. Area is approximated by 4/3. F of 3 times 3, 9, and that's 22 over 3, 20, yeah, 22 over 6. That's 20 divided by 2, 10 over 3. I should have canceled this to 11 over 3. Plus 21, 38, 19 over 3. I don't like this. I think there is an error somewhere, right? Oh, that's 30. That's 30, not 20. There we go. Because this number has to be in between the other two. You can't have 11, 10, and then 19. That makes no sense. Okay. So what do we do from here? Well, now you just plug all of the values in. Our function was square root, right? So square root of 11 over 3 plus square root of 15 over 3 plus square root of 19 over 3, and that is going to give us some decimal. Let's see. So 4/3 times, open parenthesis, square root of 11 over 3, close parenthesis, plus square root of 15 over 3, well, that's square root of 5, close parenthesis, plus square root of 19 over 3, and my calculator gives me 8.89. Now, I'm going to jump to Wolfram alpha, say integrate square root of x from 3 to 7. And computer gives a of 8.883. I mean, come on, right? We are talking fraction of a cent off with this method. And all we did is arithmetic. We did not do any calculus. Now, you can do this exactly, right? Because you can integrate this problem. Or you can use the approximation method, because approximation method works. It's just it's never going to give you exact value. All of the methods will be done the same way. You just need to know the formula. So you take your limits, which creates the interval. You divide the integral into the number of rectangles you are given, and then just plug everything into the formula and just grind through arithmetic. By the way, I like to refer to this section as the middle school section, right? Because there is no algebra, there is no calculus, there is nothing here other than just shoveling numbers. You plug in a formula and you move along. Trapezoid rule. All right, so trapezoid rule, what do we have? Well, now we are no longer approximating using constant horizontal lines. We will be now connecting the left and the right points, and that would create a trapezoid rather than a rectangle underneath. Let's have a picture for that. I can draw in this position. There we go. So let's say we have some kind of a curve over here, f of x. We want to go from A. Let's put 4 of these, let's say, all the way to B. So I have my x0, x1, x2, x3, and B is going to be x4. Now, we are going to connect these edges with a straight line like that. It creates a trapezoid. Now you are used to seeing trapezoids this way, where you have A and B and the height, and the area was given as A plus B over 2 times the height. Well, now, here's your A, here's your B, and here's your height, which is actually delta x. You see that? So I am able to do the same thing again, like before. For rectangle 1, I can write the area as f of x0 plus f of x1 over 2 times delta x, which is the height. Now you have to look at it sideways for it to make sense, but this length over here is f of x0, which corresponds to B on the trapezoids I have on the right. And this one over here is your f of x1. That's the length of that line, f of x1. So f of x0 plus f of x1 divided by 2 times the height, and the height is delta x. And now you set this up for every rectangle. Not rectangle, sorry, for every trapezoid. So trapezoid number 2 is going to be f of x1 plus f of x2 divided by 2 delta x. So on. Gives us the trapezoid formula, delta x over 2. Actually, you know what? Let me write it. So trapezoid formula for this would be We have f of x0 plus f of x1 over 2 delta x plus the next trapezoid, which is f of x1 plus f of x2 over 2 delta x plus f of x2 plus f of x3 over 2 delta x plus, and we're going to go until we run out of the trapezoids. It's not infinite. I'm going to put that in blood over here. Because you pick whether you want to have 4 trapezoids or 10,000. You can code this, put some loop in it, it's just very easy, and put 10,000 and equals to 10,000 or 100,000, and you'll get it. So now I can factor out delta x over 2, and what's left in parentheses? F of x0 plus 2 f of x1s. There's one over here and one over here. So all of these will have 2 that are in the middle. It's a very simple pattern. Plus dot dot dot, the last one is single. And that's the formula for trapezoid rule. You use it exactly the same way. Integral 3 to 7 root x dx, 3 rectangles, meaning n equals 3, right? So what do? You make your partition, 3, 7 at the end. We said that the numbers were 13 and 17. There we go. That's your x0, x1, x2, x3. So you make those when you know the interval and you know the number of rectangles or trapezoids in this case. What you do is you do the division. So b minus a over n. And each one of these becomes your delta x then. In our case, 4/3. So we have the formula. So area will be approximated by trapezoid with 3 rectangles, so T3. And now I have f of x0. That's the square root of 3. Plus 2 times f of x1. That's square root of 13 over 3. Plus 2 times square root of 17 over 3. Plus square root of 7 single. The pattern is always 1, 2, 2, 1. So the pattern, so you can have 100 rectangles in between. Only the first one and the last one will have a coefficient of 1. All of the other ones in the middle will have 2. As I was deriving that, you have seen them, right? That's f of x1. Here's x2, x2. And then x3 would have x3 in the next one, and so on. So they always come in pairs. Except the first and the last. And now just compute this mess. You know, you take your calculator and you compute this. Oh, I forgot to put delta x over 2. So that's 4/3 over 2 in front. There we go. So what is T3 in this case? Well, area is approximated by T3, which is 2/3 times, and now you put all of this into your abacus. So we have a square root of 3. Don't forget to close parentheses. If you're plugging all of this in one shot, like I am, make sure you close parentheses after every number you type in for the square root. plus 2 times square root of 13 over 3 plus 2 times square root of 17 over 3 plus square root of 7. Gives me 13.302. So times 2 divided by 3. It gives me 8.87. Right where we want it, right? Remember? We have 8.87. So, trapezoid rule, you have the formula, you plug everything in, do more arithmetic, and the answer comes out on the other side. These are numerical methods. We are not integrating, we are not differentiating, no calculus in this section. It's literally just arithmetic. Plug in numbers, move on with your life. And the last one in the bunch is going to be Simpsons Rule. And this will be quadratic approximation. So now you start fitting the curves. So you have some kind of function f of x, and you make the rectangles. And what you do is you pick the minimum number of rectangles must be even at all times. So here is another one here. For Simpsons rule, let me write that in blood. Must have even number of rectangles, which is number n. The method will not work otherwise. You will see the pattern now. So what you do, we are not going to derive it, but at least I can explain a little bit. What you do is you pick first two rectangles and you fit quadratic curve through the 3 points that you have. Then you pick next two and you fit another one there. Then you pick next three and you fit another one there. Now all of these should be on the black line, and they are not going to align perfectly, but they will be so close. It's amazing. This purple is actually terrible, so I'm just going to try and get much closer. There we go. So when you run through calculations and derivations, you are going to get that area is approximated by the Simpsons rule. Oops, approximated is a squiggle equal. There we go. Delta x over 3, and the pattern you have inside is f of x0 plus 4 f of x1 plus 2 f of x3, 2 plus 4 f of x3 plus 2 f of x4 plus 4 f of x5 plus dot 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 plus 4 f of x n minus 1 plus a single of the last one. I hope you picked up the pattern. 1, 4, 2, 4, 2, 2, 4, 1. So you keep alternating 4 and 2 in the middle, and it must end into 2, 4, 1. This is why you must have even number, because it always has to go 1, 4, 2, and it has to end with 2, 4, 1. Well, if you are forced to always have odd number of values for the pattern, then that might mean that you have even number of divisions, because even number of rectangles, because it's always the difference between them is always 1, right? You have one rectangle, 2 sides. 2 rectangles, you have 3 points, right? For 2 rectangles, you have 1, 2, 3 points, but you have 2 rectangles. If you have 3 rectangles, you have 4 points. They're always off by 1. And that's the reason why you always have to have the n up there. So now we can go back to our problem, but this time around I will have to use 4 rectangles, because I'm not allowed to use 3 rectangles like I used to be. So now 4 rectangles. 4 rectangles. And we have, what do we have? We have divisions 3, 4, 5, 6, 7. Rectangle number 1, rectangle number 2, rectangle number 3, rectangle number 4. So we have 4 rectangles, and here's my x0, x1, x2, x3, and x4. My delta x is 7 minus 3 over 4 rectangles right now. That's 4 over 4, which is 1. So area is approximated by the Simpson with the 4 rectangles. And that's going to be what? Delta x divided by 3, that's 1/3. And in here, what do I have? We have a single f of x0, which is 3, plus 4 f of x1, which is 4, plus 2 f of x2, which is f of 5, plus 4 f of x3, which is a 6, and finally plus single f of 7. So do we see the pattern? 1, 4, 2, 4, 1. 1, 4, 2, 4, 1. It's always that pattern. You always start with 1. All of the methods always start with 1. And then midpoint has the midpoints, right? They're all singles. The trapezoid is 1, 2, 2, 2, 2, 2, 2, 2, 1. And Simpson is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Always ends with 2, 4, 1. Here's your 2, 4, 1 ending. And all we need to do now is to plug this into a function, and we're done. So area is approximated at 1/3 of what? Square root of 3 plus 4 square root of 4 plus 2 square root of 5 plus 4 square root of 6 plus square root of 7. You plug that in. So you plug. These popcorn are choking me now. Let me see. We have open parenthesis, square root of 3, close parenthesis. Didn't take a square root. There we go. Square root of 3 plus square root of 4 is 2 times this, so plus 8, plus 2 root 5, 2 square root of 5, close parenthesis, plus 4 square root of 6, so plus 4 square root of 6, close parenthesis, plus square root of 7. Close parenthesis, everything divided by 3 gives me 8.8826. 8.8826. 26 would round it to 3, which is what Wolfram Alpha gave me, right? These methods are insanely precise, right? And we are not using any calculus. So you might say, well, why would we learn integration at all if we can just do this? And I have nothing to answer that. I don't have anything. It's just so your computer is going to do the integration using the algorithm which you guys can write with a couple of lines of code in whatever programming language you want, and the computer is going to do that on the 10,000 rectangles. We did it on 3 or 4 because we had to compute everything, right? One operation at a time. The computer is just going to, push through this very quickly. So that could be one of your challenge questions, to challenge yourself, learn some programming if you don't know anything, because your life is going to be programming technically. I don't care which major you are. If you're in STEM, you're programming for the rest of your life. So try to code all 3 of these. I'll give you a great tap on the shoulder if you do. And then next Tuesday, we are going to go through the insanely important 8.9. I will post announcement and send the email. You do not want to miss that one because serious issues might arise in your later education, not just Calc 2, everything, because it is the one that changes your relationship to definite integrals forever. So I'll see you all in 8.9 on Tuesday.